So I'll just introduce everyone today now. So speaking today, we have Etienne from Createc. Etienne is Createc Head of Robotics. He's responsible for the technical and scientific leadership of Createc's robotic R&D. Etienne has an MSc in computer science. His recent appointment to Head of Robotics for Createc follows 5 years of experience as a research engineer in robotics. He successfully developed a welding mobile robot for the shipyard industry in close collaboration with welder operators. Joining Etienne today, we have John Crossley from the Nuclear Advanced Manufacturing Research Centre. John has been working for the AMRC for 10 years now and is the current lead of the non-destructive testing department, where they offer qualified inspection across most of the ultrasonic disciplines, as well as surface inspection techniques. Working alongside John at the AMRC is Etienne Lowe, who looks after the research and development NDT strand. Okay, so am I passing on to Etienne first?
Yeah, indeed.
If you'd like to share your screen.
Yes, is it all fine?
Perfect.
Good morning, everyone. So I'm Etienne. I was a project manager for this project, and I will take you today for the journey we've gone through this project we called mobile wide radiography using computed tomography. So just to start with, we've got a little concept drawing here. Bear in mind, it's a concept drawing, and that's how the idea came from. And I will explain you how we came to this idea. But before we get started, I'd just like to introduce a bit the partners in the project, because it was a very close collaboration with AMRC, so Nuclear AMRC, for their expertise in NDT and manufacturing. So they've participated in the project to provide a set of sample with non-flows in the weld. So we're talking about weld inspection here, and they've provided all the expertise within the project. We also collaborated with TSP Engineering based in Washington for their very long experience in manufacturing of very high value pieces, and in particular for nuclear and all the new small reactors build and others. So they provided their expertise and acted as an end user to the project, and also providing a facility to operate X-ray equipment, which we will talk about in a minute. So before we get started, also a little word on Createc, who we are. So we are a small company, a small business company based in Hocquard. So we are about 30 people, and some of us may know us for this instrument, which is measuring radiation and mapping radiation. And we've sent that to places all over the world. It's now one of our core products. But what Createc really is, Createc is a group of people that are trying to do research and development and innovation for business. So we're looking at the problem of the world and trying to come up with new ideas and put those ideas together to make things happen. So we've started doing more and more robotics, and that's what we'll be talking about. Is combining our instrumentation expertise with robotics as well. So we're trying now to deploy more and more of our sensing technology and using robotics to act in the world and innovate. So today's presentation is about weld inspection, and really the opportunity came from how can we make it different? How can we make it better? We got all those new build everyone talks about, small reactors, the current build as well, and weld is such a critical part of all this technology. At the end of the day, you got what they were, and the quality is important. It's not it's very important. And the current technique as of today, which is ultrasonic or simple X-ray imaging, and all those techniques are limited in a way, limited in the sense that they are very disruptive to the workflow, because you either have, if you use ionating radiation, you will need to take your workpiece to a specific place, or the other way around. We need to stop all production on site and get people outside of the workpiece so that you can use radiation, ionizing radiation to analyze your weld. Or as John from AMRC will highlight, you can use other technique, but they don't necessarily highlight all the flaws you can find into welds. So we thought, well, maybe we can do different, and maybe it's such a such an important part of our workflow. Let's try to rethink it, and let's see with our knowledge and technology how could we make that different. So we propose that project for what we call in situ deployable. So that's concept again, but the idea is to provide a solution for which we can do CT directly on the workpiece, safely as well with robotic solution. So by CT, it's for people who are not aware. So you can get X-ray images where you take a simple 2D image of a weld, which will give you a 2D image, and then if you take multiple angles, then you can have a 3D reconstruction, which is a CT scan. I mean, I'm sure everyone has been aware of CT solution for brain scanning, for example. It's exactly the same thing here. So how can we use robotic to provide CT scan directly on the workpiece without being disruptive to the production line? So with greater safety, more controlled safety, which will be a gain in productivity, but also, being able to provide digital evidence to those well, because at the moment a lot of all of that is paperwork, and we were just talking with ONR not so long ago, and when ONR or such organization have to trace a big problem in weld in the nuclear industry in particular, but welds can be found in submarines and all sorts of places. When they have to trace back the information, it's all paperwork, and it makes the process, I mean, not all, but mostly, and it makes the process very complex. So, so with using digital technologies such as robots and all those scanning solutions, we could provide on top of that very good digital evidence that any end user could provide to their customers directly with a weld, such as TSP engineering, for example. If they were to use such technology, they would do their weld, scan their weld with the technology, and provide a strong evidence of the quality met. So how did we do that? Well, it all starts with robots to start with. So here the robotic system we've put in place. So I'm gonna run through how we approached that problem and how we did our testing and what we've designed. So we started with robots. You can see this robot for those who are familiar. They are not big industrial robots, big scale industrial robots. We call them collaborative robots. So they got a couple of advantages for us to use, and that's what we had available at Createc. One of the advantages of collaborative robots is they are designed to be safe to work alongside human, which means they're also safe to work alongside anything, because basically they stop in case of any collision. They got force measurements in all their joints, etc. So if you were to think, deploying such system on a workpiece on a shop floor, you would want this kind of feature. You do not want to put a complete robotic cell around your workpiece to then do your CT scan. So using this kind of technology did make sense to us back then, and we wanted to use that. However, that's one of the limitations that we quickly found out within the project is using those robots. They are all well and good. They're safe. You can operate them without any safety fence, and they will stop if there is any collision, which is very useful. But they are very limited in their payload. This Hocquard orange robot you see is limited to 14 kilograms, and that's more or less the biggest you would do with a collaborative robot, because then it starts to be difficult to stop in time to not hurt any operators or whatsoever. So this limitation limited our X-ray source we've been using, that we'll present in a minute. And so it constrained the project in how much we could penetrate in terms of weld, and how much we could play around in terms of payload. So we realized now at the end of the project that in the case of big workpiece, you probably want some bigger robots. The reach as well is limited. As you can see, those robots cannot reach that far, and you see it in one of the videos that the reach of the robot is limited, as well as the accuracy. because they're safe to operate. They are little less accurate than the digital robot because their repeatability is very close to standard robotics, but they are a little less because they need this compliance within them to be safe. But overall, we've built a very nice system together. So you can see this robot, one robot and two robots. One of the robots is carrying an X-ray source, just here, 7% in a minute. The other robot is carrying a sensor pack with design, which has a detector and 3D scanning capability. And right in the middle, you would put your workpiece. So bear in mind, this is a very R&D project. So we started at a quite low tier. I mean, we started from a drawing realistically. And so we started at a low tier, and the idea was to put this system together to learn as much as possible and towards a product in the future. So that's the robot part. Then on the X-ray. So obviously, to do a CT scan, we need X-ray. So we need to be able to fire an X-ray onto the workpiece and analyze that afterwards. So we've used this equipment from AMRC. So it's a 130 kV maximum voltage output for an X-ray for the node. It's a micro focus type. So bear in mind, you get a focal spot size of 5 micrometers. So bear in mind, it's a tiny, almost like a laser beam. So it's not spreading. One of the idea of this project as well was to try to think of the safety we would have in the future and try to not scatter radiation all over the place. Because if you want to work alongside your operators to a certain extent, obviously, you would want to have very limited. You would want to have a very limited scattering of X-ray. So for that, we designed a little collimator. You can see here in the hope that we could reduce the radiation scatter. Unfortunately, we didn't have time to test that. This project has been, as everyone has been impacted a bit by COVID and being able to do all the experimentation we wanted to do. But we've designed a little collimator, and in the near future, we hope to be able to measure how much we're scattering radiation. Apart from that, yeah, we've got a very easy to operate X-ray source, which is firing a very tiny beam of X-ray onto the workpiece that is then captured by a sensor. So that's the sensor we've been using. Obviously, that's not what we're looking at. That's a downtown sensor. So that's why I've put that image. It's just for concept and just for showing where it came from. One of the advantages of using such technology, is that instead of buying those very expensive X-ray panel or the digital solution, those little cameras are very cost efficient, and that's one of the aspects of this project we've been looking at. Doing CT scan for your workpiece or having a CT bay facility is extremely expensive, and not many can afford that. If you think of labs or small labs, etc., there's plenty of people who would like to have a CT scan capability, but it's just not affordable. And if you want to go to a special facility, then you have to go there every time. You have to move your equipment, etc., etc. So if we could provide a cost-efficient way to do CT scan with robots and such sensors, that's a win for us. So we've been looking at this tiny little detector. So you don't see the scale here, but it's just about a few centimeters, and it's very high resolution, so it gives very good imaging, and again, it's very cost efficient. So that sensor is embedded in our sensor pack, as I mentioned. So you can see it is actually just behind that C logo. That C logo is mainly here for being the target because you cannot see X-ray and things. For us, we were playing a bit with light and laser at the beginning. But the sensor pack is, sorry, apologies. The sensor pack is composed of 2 parts. So the first part would be that bottom sensor where I told you there is a little CCD sensor to detect the X-ray image, and on top you get a 3D sensor. So it's a 3D sensor that we use to 3D scan the environment. Here is just an example of the kind of 3D scan you would get. Being able to 3D scan the environment, for a robot and for a robotic solution you're deploying here and there in different places is extremely useful, because the robot must be aware of the environment and its surrounding in order to avoid collision. But the robot also should provide scanning of the workpiece so that the operator can go and select, oh, imagine you got a very long piece, right? Workpiece. 1 meter, 2 meter of weld, you're not gonna do everything in a row. So you scan the environment. That's how the process would go. You scan the environment. Once you get your scan, the operator would come and go and say, "Oh, I want to scan the weld from here to there," and the robot will automatically compute all the necessary motion to go and scan that weld piece. So some mild result on that, the sensor we've been using, which is a Nicer Kinect by Microsoft, which is widely used in the industry all over the place for 3D scanning. It's quite brand new. It's quite good at mid-range, but you can see here at close range, it's a like resolution for us, which is a bit of a problem. So you would need to combine such technology with another type of sensor or with some cameras, etc., to provide very good 3D scanning. But 3D scanning wasn't the purpose of this project. It was there as an example of demonstration, but it's quite well covered in the literature. So we didn't push that technology so much. So we're dealing with weld. So one of the it's little details, but it's quite important when you want to make products. A lot of welds are very shiny, for example, because people are grinding the weld and metal is grinded and polished in some occasion. So you know, because these 3D sensors are laser based, it's not very good for shiny surface. That's why we believe it should be combined with other types of sensor to give very photorealistic option to the operator, so that the operator can see exactly what part of the weld you want to scan. Robot calibration. So one of the important parts of that project was to get the robot to do synchronized motion, because you want to do a CT scan, right? So you want to go all over your workpiece, and so it may sound natural for, but oh well, they're mounted like that, so they know where they are to each other. But that's not true, you know. Each robot is not aware of the other robot. So if you want to make sure that every time you do a motion they align, you will need to make sure they synchronized and calibrated well. So there are a couple of ways to do that, and we've used a couple of technologies. So one of the simple solution, which is quite efficient, is to use that 3D sensor to scan the part. One of the other solution, which is shown in the video here, so is to get the robot to touch each other. So that's a fairly fast and efficient method to do. The operator can do that by hand. You'll see it in a minute. You just get the two end effector to touch to each other, and then the system self-calibrate. So two methodologies were developed within this project, and both have been proven valid, which is touching each other end effector or self-scanning robot to each other. So here you go. So the operator, thanks to this kind of technology, the operator can literally grab the robot and just align the robot to each other, and then one will self-calibrate. So obviously, because we want very good calibration, you will do that thoroughly and make sure that everything is really well aligned. Sorry. Collision avoidance. So we've done a bit of work on the, you know, if you want to deploy your robot onto a real case and onto a shop floor, you would want collision avoidance for the robot, just so that you avoid any potential damage and such. So the video you're seeing here, just been mine, it's not the same setup. You can see the same robot. It's just we used a different setup to do the demonstration. A robot was mounted upside down on a gantry, but imagine it would be the same on those two robots. So what you're seeing here is a scan of the environment, but compared to the previous one I showed a minute ago, the idea of this environment is not to be photorealistic, so that the operator can have a good idea of the environment, but it's an environment for the robot. So you can see it's kind of a Minecraft type style of environment where the measurements are much rougher. So you get those cubes instead of having very fine measurements, you get those cubes because technically the computation to compute a 3D environment and a 6D motion for the robots to avoid collision is actually not that much of a trivial problem. So you need to have this rough but detailed enough representation of the environment so you can avoid collision. And what you're going to see here is basically the operator is trying to manually move the object to somewhere. Oh, that's not great. Sorry, I got my computer crashed. Can everyone still hear me and see me? Could someone let me know if you can still hear me, please? I just had a little computer crash.
Yeah, it's all fine on mine, Etienne.
All fine, great. Thank you very much. Yeah, it's just a little crash. So you can see the operator trying to go toward that object, which would create a collision if it was going to do there, and the software just automatically prevents it to do any of that. Oh, sorry. Synchronized motion. So we got the robot calibrated. The robot can see the environment and avoid collision. So the next step is really to get those synchronized motion within the robots. So the video is not sped up, I think. Yeah. The video isn't sped up because simply you would take when we do measurements of a workpiece. So that was one of the trials where we were looking at the tiny 5P, for example. We do very long exposure, fairly long exposure, and everything is controlled. So sorry, I should have speeded up a bit the video, but just to show the example of what kind of motion you would get, and so you would orbit like that around the world, really. I'm just gonna speed up by hand, really, because it's gonna be a bit long otherwise. So you would take different measurements like that around the world. So here it's done along one motion, one horizontal motion, but you would do it in all directions. So you would do up, down, all the angle possible, because one of the idea to produce the best CT scan as possible is to get as much angle as you can in terms of images. So yeah, so you can see here the robot is orbiting in one direction, and if I can comment as well, you can see that robots align every single time, and that's when you will capture an image. So every time the robot moves, they move in synchronization. Of course, they won't necessarily arrive at the same time, but they only capture images when they're both sure they're well aligned. And in the case they don't align, we also got a several routine so that the X-ray stopped automatically, because that's the worst case scenario. Realistically, if you were to be on a workshop and you got your detector which capture all the X-ray data here, the X-ray beam, and try to avoid as much scattering as you can. If your detector, your other robot, would go all A1 and just move outside of your detector, then you would literally scatter a massive beam of radiation outside the environment. So there's a couple of routines to avoid that. We've also designed a little safety detector, but we couldn't test it, unfortunately. So just a little piece of electronic that will cut out any X-ray if it was going outside of that detector. So synchronized motion, so the robot can orbit all around. It can do all sorts of motion. Obviously, we got the constraint of the robot size, which has been a constraint within this project. But once you got that, you can do some X-ray data capture. So we started not looking at welds. We started looking at a couple of little metallic objects just to get to learn how we could use the system and then produce images. So that's one of the first good images we had. So before I show any of the results, I'd just like to highlight that, unfortunately, due to COVID and a lot of health and safety procedures, we had to comply with a lot of health and safety procedures at TSP Engineering. So we had to update all our risk assessment, local rules, and all those sorts. We started experiment extremely late in the project. So we started experiment just in last August for a 15 months project. That's a bit short. Well, that's how this project goes. I mean, it's R&D. We've developed a lot of things already, but I'll show you a couple of extra results we have. But bear in mind, we haven't finished processing all that data, so we capture a lot of extra data, but we haven't processed all of it yet. And so yeah, just wanted to say that little note. So what you're seeing here is just the top part here of the engine. So it gives you a good idea of scales you do. So if you wanted to scan a piece like that, you would actually need to do a fair amount of motion. So you would orbit around a lot of different points to capture data. But that gives this very good high resolution image, X-ray image of the workpiece. And you can see different shades, different things. You can see the inside actually of the workpiece. So I'm going to show you a few data sets we've taken. So here is a 5 penny, for example. So you can recognize. It's difficult to interpret X-ray image. I mean, if we had a CT scan to show, and unfortunately we haven't process the data to a point where we can provide CT scan, which we are very sorry for. Today it would have been great to show you a CT scan of such, but let me explain also why we haven't been able to do a CT scan. We tried, but as you can see, it's all moving a bit around. So it's very fine resolution. So it's not moving that much when you think about it, because we are looking at very fine resolution, right? But 2 points is it's obviously already a problem. Sorry, it's already a problem to produce a CT scan, because nothing is perfectly aligned. You know, you would need the image, or you would need a sufficient amount of post-processing to make sure that your image is aligned correctly. And what you're seeing here is just a robot sliding off a little bit. So that's only due to all the inaccuracy of the system. So during the calibration process or during this synchronous motion, you accumulate little inaccuracy, and that's the limitation of the system with design. We now realize at the end of the project that with a very strong build, we're confident we could do it. Very confident we could produce a CT scan, but we will need a bit of a stronger build than what we are showing today. So here is another workpiece, just a sample piece. So we're gonna try to post-process the data, but you can see, so it's basically orbiting around here. That's what the image you're seeing. So it's scanning that little C data here. And here another one where you look at, well, it's a NDT, or more for the purpose of the image, but yeah, you can see that that's the kind of image we have. So I wish I could show you a Weld piece and a Weld sample, but that's also as I said earlier in the presentation, that's also the limitation we found out, and that's what we do this R&D project, is to learn as much as possible and iterate every time to try and get better every time, and then, you know, get to a final solution. Is really that limitation of payload and robot. So the source we've been using is 130 kV, but only about 200 microamps. And one of the problem with that is to be able to penetrate a weld. So it will take a very long time, about half an hour with our beam, to be able to just take one measurement of the weld. And given the fact we started experiment in August, we just didn't have the time sufficient to take sufficient image and get image X-ray image of the weld piece we are looking at. So a bit of a shame, a bit of a frustration, because we got all this very great robotic system in place and the sensors, but we couldn't get to a point where we get X-ray image of the weld. But we got data set to play around with, and those data sets, even though they are sliding off a bit, are very good input for us to look at how we can then post-process the data and do the necessary to produce a CT scan. So the learning, just a quick summary of the learning we've done on that. So yeah, as I said, calibration of the system is absolutely essential. The method we've used are really good and give fairly accurate calibration of the system, but we believe that you would need even more accurate than that, because we're working with such small and high resolution of measurements. You really need to master that calibration step. So you would need a stronger build and a thorough routine to align the two robots together. The workpiece as well. So you've seen that, you know, we just put that on a metal beam, central metal beam, and put our workpiece like that. Same again, that will need to be very accurately positioned. So you would do that either manually through manual measurement or through the 3D scan, but need with better accuracy, so to make sure that all the distance between the source, the robot source, and the object, and the distance between the object and the detector are well known, and those are very important for CT scanning. You know, it's parameter you can play around, but they're very important. One of the limitations of our system and our designs, but we know how to improve it now, will be also you need the detector, so that little black sensor I showed you. You will need the detector to be very close to the workpiece, so that you can get the best image you can. But that obviously needs the reach of the robot. Imagine you got a workpiece like that, or a curve or whatsoever. The number of different angle you can take on that measurement are quite limited by the size of your sensor. So you would need a very narrow sensor with very sharp edges and just a tiny bit, so that you can do as much angle as you can around the workpiece. So those are great learning, and that's why we go through this experimentation, and we really strongly believe that the next step for this project will produce a whole bunch of good data. But before I talk about the next step of the project, I'd like to invite John from AMRC to talk a bit about the studies they've done on Weld NDT, and they've done a very, very useful and great work at looking at a set of samples with non-defect and all the different NDT methods. And then the work they've done can really be used for anyone who wants to do what we've been doing through that project, which is trying to provide new method to do NDT. So John, I think the best is I go through your slide and you just tell me to move on whenever.
Yeah, thank you, Etienne. I'll just give a quick introduction. So my name is John Crossley. I work at the Nuclear AMRC in Sheffield. We supported Createc on this bid. The idea being 12 to 18 months ago, we were going to create a system that would potentially be able to go through the thicker section welds that we did here, as Etienne's led to the actual test pieces, and the source wasn't powerful enough to create and get through our test pieces. But that's not to say that these won't be back into service at a bid at a later date, as this system gains traction, and we follow up on that. So if you want to just click on, please, Etienne. So the Nuclear AMRC, we looked at creating several test pieces. We created those in a carbon steels, and we also created them in austenitics. We looked at the vast majority of cracking mechanisms to reproduce cracks, lacquer fusions, laminations, all in small test coupons. As you can see in the picture, that's one of 15. This was a base funded project. I mean, these coupons are available to anyone that's got a system that would like to trial out their system. The idea of these coupons is we did the fingerprinting operation across all of them and compared the vast majority of current capabilities here at Nuclear AMRC. So if anybody does need these and has a system that they think they could test their system against using these coupons, please get in touch with me. I'll put my details in the chat. I don't know if we're going to share them after this presentation, but I'll certainly put them up in the chat. So anyone take those details and please get in touch if they need them. So if you just want to click on Etienne. So yeah, so the idea of the Createc system was to take the CT scanning into a mobile system. So we've got on site a whole range of technologies here. Sorry, I should just turn on my camera. We've got a whole range of technologies here at the Nuclear AMRC. So all the coupons that we produced they underwent CT scanning in our own chamber, which you can see on the bottom left of that slide, and we collated all that data. We also ran those in current ultrasonic formats. So they would, we created a little scanning jig, which is on the top right, and we did the phased array and time of flight inspection of those coupons. All those inspections were done kind of to a code compliant inspection, so we can always trace those back. We know the defect size, height, and what we did is at the end of that, all our reports is collated all the different technologies, and we looked at those for floor start, floor length, floor height, and we did a comparison across all of those technologies. It was unknown to myself at the time. We didn't know if say ultrasonics would always size a floor slightly longer, or obviously it's known within industry that TOF's really good for floor height detection. against phased array, which is not as accurate. But we're only talking to points of a millimetre. But if we just click on Etienne, so all the test coupons went across there, and as you can see, I mean, the floor length, there was some undulations, but I think we're talking in very small figures against where you would consider the recorded floor length of a defect. A lot of the times in industry, these floors would then be taken out by a grinder. So the 1, 2, 3 millimeter discrepancy over floor length is acceptable. What we also found is there was no real trend across floor length. Floor start, you can see there's little bits of a trend, but there was nothing there that we would really point to. I think of review of the data, there was certain things where our scanners for ultrasonics, I don't know how many of you are aware of ultrasonic scanners and ultrasonics, but as you start to scan a test piece, before the encoder kicks in, you have a little bit of flex in different scanners. So I think maybe these some things to look into there to make sure that the flex is always taken up. But again, we're talking really small discrepancies for the types of floors that we've been looking at. So like I say, these test coupons all exist. They will all be stored at the Nuclear MRC. If anybody's got technologies that they think they could trial against these, this Nuclear MRC side of this report it's an open document. It will be ongoing, and the more technology we can put in there, we can start to populate these tables. And yeah, I mean, that's a real quick roundup of what we did there. Createc did the most work in this project, so obviously that was led to Etienne running this presentation. But I will put up my contact details, I think, at the end of this, and if anybody does need me or wants to come and see what the Nuclear MRC is about, or have a chat about how we can help you, then certainly give us a call. We don't just have NDT in here, we've got a large section of welding, looking at multiple joining facilities, and we've also got machining capabilities. So like I say, I'd like to thank Etienne at Createc for working with those guys, and also TSP Engineering, who are not on this presentation today, but they provided the end facility for which Etienne was able to conduct his experiment in. And that sums up my presentation. Like I say, I'll hand back to Etienne, and thank you all for your time.
Thank you, John and Etienne. If anyone has any questions.
We had a bit of a conclusion, if you don't mind. We were able to finish the presentation, sorry. Let me stop my video again, sorry. Yeah, that's a bit of a conclusion, and we got a little video. Thanks a lot, John, for all your work, and again, Createc has led the project, but I'd like to say that, and that's my conclusion really, is really by collaborating with all this range of expertise, from end users to people like AMRC and expertise in manufacturing. It's not only NDT, they got a whole bunch of welding machines. That's a very impressive workshop, I must admit. And people like us who try to innovate, it's really combining all these forces together and learn to work together and bring different expertise. That's how we do innovation. That's how we do this project, and it has been really wonderful. And that's one of the great outcomes of this project is now we have very close collaboration with the Nuclear AMRC and TSP Engineering, and the work we've been doing here and we've presented is only a start for us, and that's really the great learning. We haven't completed all the results. We haven't done everything we wanted to do, in particular regarding the CT scan and measuring radiation scatter and the safety system. But we've learned a great lot, and we know exactly what are the next steps for this project to carry on, and maybe see the technology happen in the real world one day. Because that's why we do innovation. It's for business. We don't do research for research, even though that's needed in time. We really try to get our technology outside in the real world. And then that's it really. That the future work will be doing. So the idea is to validate our methodology and do the real next steps, and demonstrate how you can produce a real CT scan on a workpiece such that John presented. And so we've put a proposal actually to carry on the work. But if anyone is interested here to join this journey of doing a bit of a revolution in NDT, because the technology will potentially show defect or provide a workflow that is very different to how we do things today. And instead of having to do a weld and do your NDTs and having to grind a weld and do all over again, which has a massive cost and is a problem, you could do welding and straight away the inspection. So instead of going, you could do one welding pass, do your inspection, one again, and that's the work we'll be looking at with nuclear AMRC. So we haven't got the proposal in yet, but we received 4 letters of support from the end users, and hopefully we'll be able to carry the work with nuclear AMRC and this company based in Bristol called Iona Sensor, which does external tracking. So it's a UK company doing external tracking, and we'll be looking at using this external tracking to prove the safety of the system. So just before we conclude everything, we got a little video. So it's a 5-minute video, but I think it's worthwhile to run it through. I don't know if the sound is in my sharing. So if someone can tell me if the sound works on their end, that'd be really good. Do you have sound?
No, we've got no sound as yet.
Is there an option to share with sound, or is that not possible? Does anyone know?
There should be a share computer audio at some point when you share screen, I think. There should be a checkbox for sharing computer audio.
Sharing entire screen window. Sorry, share tab audio. Yes. Yeah, apologies. I'm on. I'm not. Yeah, I think it's because I'm using the web version, unfortunately. Well, in any case, that would be teasing for later. The video is going to be uploaded on YouTube anyway. So I invite everyone to stay tuned, and you'll get the video soon enough, if not a week, on YouTube on Createc's website. So just a little video to summarize what we've done. You've seen everything anyway. So that's about it for our presentation. And if you have any question or want to discuss anything, feel free to do so in the chat.
Thank you, Etienne and John, for your presentation today. So as I said, if you've got any questions, please pop them in the chat box. So we'll just give that a few minutes. Well, I've got a question for now, Etienne. For the feature size of the CT scans,
Yes.
what sort of feature size was it? Was it like microns or?
On the detector, you mean?
Yeah.
Yeah, so it's 20 microns resolution on the image. So that would be more than enough to see the defect. As John highlighted, we're looking at the millimeter defect or this kind of size, so we believe it would work fine enough in terms of resolution. Obviously, that has yet to be proven, but John, if you want to comment on the CT scan you've done, that would be the resolution we're playing with will give sufficient resolution, right?
Yeah, because I was going to ask also then, sort of like what size, I guess, of damage or anything could be seen as critical if it goes down to like 20? Would it be like less, or usually would it be if they were smaller, it wouldn't cause much of an issue? You
mean in the defect we find, right? Yeah. If they were smaller than that resolution. I don't believe we're in the industry defects such as smaller as 20 microns are looked at, especially on welds that are a couple of inch size, And here we're talking we've presented the system on a very small scale, the small test piece, but the idea is to scale up everything to much bigger workpiece. So you're looking at a millimeter weld defect, usually not microns. So that wouldn't be an issue, I believe.
Okay.
Yeah, just to back up what Etienne said there, when we're looking at the inspection within the new AMRC, a lot of our inspections are done across a reference standard of a 2 millimeter side drilled hole.
Oh.
So the sound would, if you imagine a 2 millimeter side drilled hole straight through a component, and the sound beam would hit the radius of that 2 millimeter side drill hole. So microns to 2 millimeters, the sensitivity of the system is well within that.
But it's also one of the claims of the project, and it's one thing we'd like to see, that if we are to produce very accurate CT scan like that, what can we see in the world? How much can we see? How far can we push the technology? And can we see defects that are sometimes missed with other methods? So that's why it's all very exciting and also frustrating not to have the results yet.
Yeah. I think I've only ever seen CT scanners in big rooms taking up a lot of space. So it's very cool to see how mobile they are and how small really they are. When you take the CT scan, how do you avoid the radiation then? Do you just have to leave the room, just set it up?
Well, at the moment, that's how it's done. That's correct, but that's not what we would like to do in the future. So obviously, we're working with radiation here, so we have to go through a whole bunch of safety, and that's why we use the X-ray bay, which is literally a bunker. But the claim and what we'll be looking at in this new proposal and carrying on the work is really that safety aspect of Weld, which is can we reduce the scattering of radiation, and by making sure constantly with a whole bunch of safety and different safety levels, how can we ensure the robots are constantly aligned and if they are not, cut off the X-ray fast enough so that it's not damaging to operators around. So yeah, it is our strong focus for the next steps. Safety of this technology. See if one day we could deploy it on a nuclear AMRC manufacturing shop, for example.
Yeah. We've got another question that has come in now, and it says, in terms of detecting weld flaws, how does the robot and X-ray system compare to something like the TWI teletest focus guided wave technology?
So I'm not very aware of the TWL. I don't know if John, you know about the technology. I'm sorry, I'm out of my expertise here.
Yeah, I mean, I don't work closely with the guided wave technologies, but all of the coupon manufacture that we did within Nuclear MRC, all of the flaws were detectable by our CT unit. So we would expect, as we scale up the MWCT systems, we would receive the same sensitivities. I think it's worth pointing out that there were certain areas where, and it's in the report, there was some technologies were better at finding some defects than others, whereas CT scanning saw all of the flaws because of that ability to navigate around the part and create that three-dimensional image, whereas some of the inspection technologies with NDT and ultrasound are only approaching welds at limited angles. So it's all about, it's not always a one size fits all process with NDT. A lot of times with ultrasound, you couple that up with a surface inspection, so you carry out 2 inspections. So if the ability of the MWCT, as we move that forward, can eliminate surface inspection and bring surface inspection and volumetric inspection together, then you've got the complete package. Of course, governing all that is the codes and standards behind that. So they won't always be, I mean, this technology is not going to jump in there in the next year or so. But as we process it and move forward, you'll probably find that some industries will adapt quicker to this kind of technology than others. Certainly, as Etienne alluded to, we're using an X-ray source, so the weld thickness is always going to be limited with an X-ray source, yes, up to about 20 to 30 mil, you can hold an X-ray source relatively easy. Beyond that, you start looking at cobalt sources and things like that, which is what obviously this system is built for. So it's the thinner end of the market and the thin end of the Weld section.
Exactly, yeah.
Around that.
Thank you. I was interested to know as well, with the 5p piece that you scanned, how long does it take to do the scans for?
Not very long actually, because the 5p is not much metal to go through. It's a couple of minutes really. Everything was done manually so that we control the process, but we got all automated routine, and if we ran the automated routine, it would have taken 5 minutes max. But it all depends of the time of exposure. The bottleneck here is not the robot motion. The robot moves very fast. So that's not the problem. It's how long you need to expose your weld or your workpiece to take a good image. So if you go to a weld workpiece and you have an X-ray source like ours, which is a bit limited, you would need very long exposure. That's why we didn't go through that experimentation, because a single image would probably take an hour. And if you multiply 1 hour by the hundreds of positions you're taking, you're talking about an experiment that is more than 100 hours per experiment. So that's why we believe scaling the system to higher source is a bit more valuable than going through hours of experiments, just because of the limitation of our technology here. Does that answer your question?
Thank you. Is there any more questions from anyone else? If you'd like to put them in the chat box. Okay. I think that might be it for now. So I'd like to say thank you to our speakers today, Etienne and John.